What's up guys, it's Samar Fiaz and today's video is on AQA AS Level Chemistry, June 2016, Paper 1. Question 1.1, give the full electron configuration of the Al atom and the Cl3 plus ion. So the Al atom has 13 electrons, so it's going to be 4, 10, 12, 3p1. Perfect. And Cl3 plus ion, well, it's a chromium atom, but it's got 3 plus, so it's an ion. So it's 24 electrons originally, but then a minus 3, so it's 21 electrons. So it's 1s2. Twenty-one electrons, right? So 4, 10, 12, 18, 22, 21. So then 3p6, 4s1. What happens is, instead of that, chromium's got a special rule. Instead of that, what happens is you get 3d5. No, sorry, 3d3. Because 4, 10, 12, 18, I want 24. So instead of 4s2, 3d1, it's just going to be 3d3. So 1s2, 2s2, 2p6, 3s2, 3p6, 3d3. You just form of the ion as a charge 2 plus same electric configuration as krypton. So krypton, 36 electrons, 2 plus charge, so it's going to be SR2 plus, because they're minus 2 electrons, and then you get same electric configuration as krypton. Use the formula contains 2 plus ions and both have same electric configuration as argon. So 2 plus ions, argon, 2 plus, so it's going to be Ca2 plus, yeah. 3 minus, argon's 18, so it's going to be phosphorus with the P3 minus. And then what happens is you just swap them around, so then it becomes Ca3 P2. So not a bad question, just testing how well you know electron configurations and juicing formulas. Juice which of Na plus and Mg2 plus is a smaller ion. Now if you look at Na plus and Mg2 plus, sodium and magnesium, right? Na plus, Mg2 plus, well, the smaller ion is going to be Mg2 plus. And if you look at the explanation from Mark's team, it is very, very similar to what I would say. More protons, but you also need to say with the same shielding. So, because Mg2 plus has more protons with the same shielding. An equation for the first ionization energy of sodium, so Na plus gaseous plus E minus, and then you've got Na gaseous here. Yeah, it's always in its gaseous state, except for the electrons, obviously, they're not in a gaseous state. Completely going by plotting the approximate first ionization energy values for magnesium and sulfur. So, magnesium and sulfur, well, obviously here, in order to go from here to here, what's going to happen is it's going to go up and down, and up and then down. So magnesium, I would say around about 800 to 1000, 600 to 800. Sulfur, sorry. So 600 to 800, yeah. not 800 to 1000, or I was thinking somewhere around about here, because then it goes here, then down and there, and then sulfur, the 16 electrons, that would be 1000 to 2000, so that could be, I don't know, here, then slightly down there. Yeah, 800 to 1000. We'll explain about the first ionization energy of sulfur is different from that of phosphorus. Now, what you need to do for this is, if you don't know these examples, you know, nitrogen and oxygen, sulfur, phosphorus, beryllium and boron, all these examples, which you probably aren't going to remember all of them. Look at the electron configuration and you'll find out why the first ionization energy is different, is lower, is higher, etc., etc. So with sulfur, it's got paired electrons in its p orbital. It's 3p orbital, so that's the first thing you say. Electron paired in sulfur's 3p orbital. Paired electrons repel. Repulsion means less energy needed to remove those electrons. Electron paired in sulfur's 3p orbital. Paired electron repel, so less energy needed to remove electrons. Question 3, calculate the mean titer and then use it to determine the mole of HCl. Mean titer 0.1 centimeters cubic in inch, so these two, so it's going to be plus 9.65 divided by 2, and that will give me 9.70 centimeters cubed. And then it says use this value to determine the amount of moles reacted with this much MHCl CH3 solution. Of HCl, so it's going to be the concentration times by that, so it's going to be 0.102 times by 9.71 divided by 1000, 9.89 times by 10 to the power minus 4. Perfect. Then it says calculate amount of moles of MHCl3 in 250 centimeters cubed solution. Well, MHCl3 and HCl have a 1:1 molar ratio. So whatever the moles of HCl is, that's the moles of MHCl3, vice versa. But the thing is, in this case I want it in 200 centimeters cubed, this 250 centimeters cubed, in this case it was 25, so I need to times that by 10. And then that will give me 9.894 times by 10 to the power minus 3. And then calculate experimental value for the MR, well, Moses mass over MR. Moses mass over MR, MR is the mass of MHCl3, this in grams, so 1.464 over my number of moles, which I just worked out. I got 148. Perfect. Using the same operation suggests a procedure could prove to reduce the percentage of certain using the burette. Use a larger mass of solids or larger titer / reading will be needed. Got a method to prepare the solution. So 6 marker Three stages. Stage 1 transfers no mass solid. Weigh the sample bottle containing the solid. Transfer to beaker, reweigh sample bottle. Stage 2, dissolves in water. And all you can say for this case is add distilled water, just deionized water rather. Add distilled water, stir with a glass rod until all of solid has dissolved. Stage 3, transfers, washing and agitation. Transfer to volumetric class. With washings, make up to 250 centimeters cubed. And final step, shake / invert / mix. Yeah. Question 4, in terms of instruction, boiling experiment, boiling point of bromine is different from magnesium. So if I look at the boiling point, I can see magnesium has a significantly higher melting point and boiling point compared to bromine. So why is that? Well, bromine is Br2, right? And that is simple molecular. Magnesium is a metal. It's got strong metallic bonds, and that's how you need to infer these kind of questions. They're not gonna. This is like sometimes there'll be examples that you've already learned, like silicon, etc. But sometimes they'll just give you a metal. It won't tell you it's a metal, but you need to understand that's a metal, so it's gonna have metallic bonds. That's just bromine, so it's gonna be simple molecular. So let's have a look at the mark scheme. Bromine simple molecular. Magnesium is metallic. It consists of positive ions and received delocalized electrons. Of positive ions and receive delocalized electrons. Then say bromine has weak van der Waals forces between molecules. And say magnesium. Or you could then say requires more energy needed to overcome stronger metallic bonds. Or say in this case, less energy needed to overcome the weaker van der Waals forces between the molecules. And then the final plot suggests why magnesium is liquid over much greater temperature range. I'll say magnesium forces of attraction liquid are stronger. Liquid are stronger. Question 5. Calculate the mass of ammonium flask Q. So I'm going to be using PV equals nRT. Yeah. N equals PV divided by RT, which is going to be pressure in pascals divided by the volume of meters cubed and the volume of flask Q is that. So it's going to be that divided by a million, so it's going to be 1 times by 10 to the power minus 3 instead of times by 10 to the power 3. Divided by R, which is always going to be 8.31 generally, and it again is times by temperature in Kelvin 300. Work that out. Moles, the MR of ammonia NH3 is 17, 14 plus 3, 17. So I want to find out the mass. Moles is mass of the MR. Mass is going to be moles times by the MR. And I get 0.696 grams. Perfect. Then it says when the tap is open, ammonia passes into flask B, temperature decreases by 5 degrees Celsius. Wonderful for that. Calculate the volume of flask P. So I know I'm going to use PV because I know T again. But in this case, all I care about is the volume. And I know that when the tap is open, ammonia passes into flask P. I want to calculate the volume of flask P. I've got the volume of flask Q. And if I use V equals nRT divided by P, that will give me the total volume. So N is the number of moles, which is 0.0409. 8.31 times by the temperature. Now this is a tricky part. It decreases by 5 degrees Celsius. Okay. So what's going to happen to the Kelvin thing? Well, it's just going to be 295 Kelvin. We don't care. We don't like convert this into Kelvin and then subtract that. No, it stays the same. It's just going to be 300 minus 5, which is 295 over the pressure in pascals, where the final pressure in both flasks 75 kilopascals, 75,000. Then I get that volume. Then I'm going to do this volume minus the volume of flask Q, 1.00 times by 10 to the power 3. Oh, but this volume that I've got right now is in meters cubed. So I want to convert it to centimeters cubed. So times by, well, from centimeters cubed to meters cubed, I'm divided by a million. So meters cubed to centimeters cubed, I'm going to times by a million. I've got that in a million. Then I'm going to do my answer minus 1.00 times by 10 to the power 3. And I get the volume as 337 centimeters cubed of flask P. Allow range 310 to 342 centimeters cubed. I got 337. That's in that range. That's perfectly fine. So find out total volume. Okay, and then do what I did then was convert centimeters cubed and then do the centimeters cubed minus the volume of Q, and then you get the volume of bulk P in centimeters cubed. 337 and allows that as well. Explain how ions accelerate, have detected, and have the abundance determined. By attraction to negatively charged plate, detected by gaining an electron, relative abundance is proportional to the size of current flowing in the detector. Ions detected by gaining electrons. Relative abundance proportional size of current from detector. Ions accelerate by attraction to negative charge plate / electric field. Perfect. Calculate mass of this ion. So it's just going to be 52 divided by L, Avogadro's constant, and then divided by 1000, or do that times by 1000. So 52 and then I get 8.64 times by 10 to the power minus 26 kg. And the other part says kinetic energy was that, calculate the velocity. So I'm going to rearrange the equation and get velocity equals square root of 2ke divided by m. I've got kinetic energy, I've got the mass of the 52 Cr plus ion is that, so I can find out the velocity. Square root of 2 times by 1.269 times by 10 to the power minus 13 divided by 8.64 times by 10 to the power minus 6 . 2 times by 1.269 to the power minus 13 divided by my answer, the mass of the ion, and then I get ridiculously large number than the equivalent standard form, so I get 1.71 times by 10 to the power, I know some meters per second to the power minus 1, it says right here, times by 10 to the power 1, 2, 3, 4, 5, 6. So 8.64 times by 10 to the power minus 6 kg, yes, and then 1.71 times by 10 to the power 6 meters second to the power minus 1. Because 6.4, bromine has two isotopes, approximately equal abundance. Sketch the pattern of peaks you expect to see in a mass spectrum of sample of bromine. Now this one's really challenging question in my opinion, for 2 marks. So what I would do is, okay, if I've got 79 and 81, what are all the possibilities I could have? I can get 79, 81, 79, 79, obviously BR, all of that, and I can have 81, 81, and that's it. 79, 81, 79, 79, 81, 81, and everything else would just be repeating myself. So then it'll be like, okay, I've got 79 BR, got 81 BR. And I can get 79 or 81. You could get 81 and 79. And if you keep doing that, and then you're like, that's a half. So that's got to be half. That's a half as well. And then the second one, well, then that's going to be a quarter. What you should get is 160, 50%, 158, 20% of the abundance, and 162, 25% of the abundance. It's a complicated method, but what I would just recommend is learning this method, this Venn diagram, on this probability tree diagram, and so anytime a question like this comes up with chlorine, whatever, you know how to do it just by using this diagram, by sketching it. But yeah, peaks are 158, 160, 162, 25, 50, 25. Some of xenon has AR that. Some consists of 4 isotopes. Abundance 3 of the isotopes shown. Data that is missing. Use data to calculate abundance of isotope MXE. Calculate the mass. It's going to be 100 minus 28 plus 25 plus 27. Which can be 20. So that's the percentage abundance of MXE. Right, then what I want to do is find out the mass number of MXE. I know 20 is there, I want to find out the mass number. So I can say 131.31 equals 129 times by 28 plus 131 times by 25 plus 132 times by 27 plus 20y. Let's just say let MXE equals y over 100, because it all adds up to 100. Then times by 100, so then that goes to here, so then I get 13131, so just moves here to here, equals, then I put the rest in the calculator, so 129 times by 28 plus 131 times by 25 plus 132 times by 27, 10, 4, 5, 1 plus 20y, 13131, 13131 minus my answer divided by 20, I get y is 134, so therefore m is 134. That's the mass number of it. Does that make sense? Yeah. 129, 131, 132, 134. Draw diagrams to illustrate the shapes of NH3 molecules, AlCl3 molecules. So AlCl3 is going to look something like that. NH3, well, it's going to look something like this, isn't it? Obviously with the lone pair of electrons here. So AlCl3, perfectly fine. NH3, well, I should have done it like this then. Yeah, it's going to have the lone pair of electrons in it. Then it says, so draw diagrams, which include that, illustrate shapes, including diagrams, any lone pair of electrons, indicate the values of the bond angles. So in this case, it's going to be NH3 lone pair of electrons, let's say 107 degrees. In this case, 120 degrees. Yeah. Name type of bond formed between, I explain how the type of bond is formed. Anytime it says name type of bond formed between something, it's usually always coordinate bond. And it's the same case for this one, obviously. But how is it formed? That's the hard part. What you say is then lone pair of electrons. Wait, no, sorry. Coordinate bond, both shared pair of electrons come from the nitrogen. Shared both electrons come from the nitrogen. Explain the value, changes, information of that. Well, what happens to the shape? Well, aluminium is now surrounded by 4 electron pairs, so it's tetrahedral. Is now surrounded by 4 electron pairs, hence tetrahedral. Hence bond angle decreases 0.5 degrees to 107 degrees. Oh, sorry, 120 degrees to decreases 120 degrees to 109.5 degrees. I know, obviously, then say be a bit more specific upon angle of that, but yeah, that's fine. You guys get the point. Right, half equation for oxidation chloride ions. Chloride ions will go from Cl minus to chlorine, obviously. I need 2 here, and I've got 2 here. I need 2 negative charge reductions here. Right, half equation for reduction of chlorate ions to chlorine. So you need to know the formulas of these and just how well you know this topic. It's all these equations, not these ones, but it's like chlorine, group 2, group 7. And you need to know how chlorine reacts with water and all of that. So I need 2 here. Then I need a 2 H2O here. Then I need 4 H pluses here. And then I need 2 E minuses here. Is that correct? Cl2, Cl minus 2 Cl2. I need 2 there definitely. Yeah. In this case, I don't need to times the equation by anything. Negative electrons already cancel out, so I'm left with 14 H pluses plus 2 Cl minus plus 2 ClO minus or 2 Cl2 plus 2 H2O. Where do I get 2 Cl2 from? 1 chlorine there, 1 chlorine there, so just add up to 2 Cl2. And the thing is, with this equation, it simplifies. We've all got a factor of 2 in. Right, so then that's divided by 2, so 7H pluses plus Cl minus plus ClO minus from Cl2 plus H2O. And always be on the lookout for cancelling out finally at the end. So let's have a look at the mark scheme. 2 Cl minus is Cl2 plus 2 minus, 2 E minus plus 4H plus 14H plus 2 ClO minus from Cl2 plus 2 H2O, ClO minus plus Cl minus plus 7H plus. Oh, this is. Wait, what? From Cl2 plus H2O, 2H plus. Oh yeah, why did I get? I misread this as 14 H pluses, and just because I just drew it properly wrong. That's an add. Yeah, that's supposed to be 4H pluses, and that's also 4H pluses. And then if we divide by 2, then that does become 2H pluses. Silly mistakes. Keep doing that. So suggest or observe when chloride is added to colour solution of potassium iodide goes brown. Why? Due to iodine. Due to iodine, because I minus oxidized. So it goes brown due to iodine because I minus oxidized. Question 9.1: student is given a powder made from a mixture of anhydrous barium chloride and magnesium chloride. Student dissolve this in powder in a conical flask, added excess sulfuric acid, white precipitate was formed. Identify the white precipitate. Well, excess sulfuric acid, barium chloride, white precipitate, it's going to be barium sulfate. That's probably the easy part. Then it says calculate the percentage by mass of magnesium chloride in the powder. I know that. She was given powder to dissolve this much of powder in conical sulfuric acid. The mass of soluble is down. Calculate percentage by mass of magnesium chloride in the powder. So what I would do was what I would do is find out the moles of the solid. Then use a 1:1 mole ratio to find out the moles of sulfuric acid. Yes. No, find out the moles of So I know mass is a white precipitate formed, filter off, mass is solid was that. So I can find out the moles of barium sulfate, right? 0.764 over the MR barium and 137.3, 32.1 plus 64. Yeah, that'll give me the moles. Then I know it's 1 to 1 mole ratio. I'll get the moles of that. Then I need to find out the mass of what? So I need to find out the mass of. So barium sulfate. That's first mark. Barium sulfate. If I find out moles, 0.764 with the MR. Yes. Then what do I do? Then I find out the mass of barium chloride. Alright, yeah. Because I want to find the percentage by mass of magnesium chloride. I find out the mass of barium chloride. Because the barium sulfate is going to have a 1 to 1 molar ratio with the barium chloride. Alright, yeah. So I get the moles of that. Get 3.27 times by 10 to the power minus 3. Then I find out the mass of barium chloride, which is going to be the MR barium chloride, which is barium is 137.3, so 137.3 plus 35.5 plus 35.5, 208.3 times by 3.27 times by 10 to the power minus 3. Get the mass of 0.68 grams, 0.68 grams. Then what I realized, okay, so now I've got the mass of barium chloride. I know total mass is that, so then I can do 1.056 minus 0.68. That will give me the mass of magnesium chloride, so 0.376, and then do that over 1.056 times by 100 times by 100. 0.376 divided by 1.056 times by 100, and I get 35.6%. But allow 33.7 to 35.5. I got 35.6. So alright, I did get 0.6818 grams, but I just rounded it to 0.68 grams, and that's a mistake. You shouldn't round it, because then you'd be precisely accurate. But it says do not penalize incorrect precision here. I think I'd get a mark, yeah. So 35.5% there. And that's the end of section A.